All right, so as we continue through Unit 2, we've done Chapter 4 and 5, which are all about Newton's laws. And now Chapter 6 is going to be the last part of this unit, and that has to deal with circular motion, orbits, and gravity. So it's actually more of an application of Newton's laws than it is just learning about Newton's laws. But it's a big part that is covered on the AP exam, and if you've taken a look at your practice FRQ yet, you would see it in there as well. Okay, so we are starting with a pre-lecture video talking about forces and apparent forces when dealing with circular motion. So when we talk about Chapter 6, we're talking about uniform circular motion. And uniform circular motion can be a little misleading because we're going to say that any object has acceleration, and therefore it has a change in velocity, even though the speed is constant. So you got to be careful when we're discussing these things, but we'll take a look by starting at with the pre-lecture video. Okay, so he starts off by whipping a ball around in a circle, and he recapped just what I was talking about in this video about how an object that goes around in a circle, so if here I have like a ball tied to a string, it's going with some velocity, and the overall magnitude of the velocity, aka the speed, is constant, but since the direction is changing, then the velocity itself is also changing. And so the speed, and this is what gets confusing, the speed is constant, but due to a change in direction, we have to have a change in velocity, and that means we have to have acceleration. And in this case, the acceleration is always pointed directly to the center, and it has a magnitude of v squared over r. And this was introduced way at the end of Chapter 3, and that's what we're going to be focusing on more right now. So then he continues to go through a couple different demonstrations, like having a cup of water on a platform as you're spinning around in the circle, and getting into the apparent forces that are acting as something goes in a circle. So it is a good little video. It's a good little introduction of some of the stuff that we're going to cover in this chapter. The first part of this chapter is the easy, straightforward part where we're just defining and explaining uniform circular motion. So that's where we're going to start. So uniform circular motion is just an object that's going around in a circle. So on the right side of the page over here, I have exactly that. We have this so we have this dot right here. It's going around in a circle. We can see that by the lengths of the vectors that the velocity is constant, or I should say the magnitude of the velocity is constant. So as we look over to the side, we're saying that the speed of a particle is constant, but because it's changing its direction all the time, the velocity is not constant. The velocity is changing. And we actually got this at the end of Chapter 3 in a quick little introduction, but we have this formula that the acceleration is the velocity squared over the radius of the circle. So here's my center of the circle. This is the radius. Here is the velocity. Velocity in meters per second, radius in meters. We get, and then velocity is squared, so we get meters squared over second squared over a meter. One of the meters cancel. You'll typically see me write it as this: a subscript c is v squared over r, indicating that it is circular motion, and that's a centripetal acceleration. So got a little quick check for you. Ball's at the end of a string. It's being swung in a horizontal circle. This means like it's on the ground, or it's facing the ground and it's circling above the ground, versus thinking about like in the pre-lecture video when he was demonstrating twirling it around where something's going above my head and then below my head. So if that makes sense, I can try to draw it real quick. It's doing this, there's my string, and there it is going a circle, versus this, oh wow, that was great, where it's going up and down in a circle, right? Anyway, long story short, So it says the ball is accelerating because, and the answer is the direction is changing. So it's being swung in a circle, speed is constant, but direction is changing, so velocity changes, and therefore we have an acceleration. Another quick check, car is turning a tight corner at a constant speed. Top view of the motion is shown below. The velocity vector, we're going straight right here. Technically, that's going to change as it continues to go around the circle. Points east, what's the direction of the acceleration? Well, this is the radius of curvature. And for circular motion, the direction of the acceleration is always directly towards the center of the circle. So the direction in this case is going to be south. So when we're talking about circular motion, we have to think about how we're going to describe things. Now, before, we had things like meters per second for speed and acceleration. We had all these different things that our units made sense. But now we're going to change up our vocabulary because our view has changed up. So we're no longer looking at linear motion. So we need to describe things in a new way. So the first way, we'll talk about the period of an object. And the period is how long it takes the object to go around the circle one time. We use the letter T for that, the capital letter T, and it's to go around one time or one circumference. Now, we also use something known as frequency, and if period is the amount of time that it takes to go around once, the frequency is the number of times it makes in 1 second. And these two quantities are inversely related to one another. So we can easily convert from one to the other. But these are some different ways for us to quantify and explain what is happening with the motion of the object. When I look at a tire, I don't say it's traveling at 32 meters per second. I say it's rotating at 200 RPMs or something like that. That would be an example of a frequency. Or it takes a tenth of a second to go all the way around. That would be a period. Thinking back to Unit 1, I know that velocity is distance over time. So my distance in this case is 1 circumference, and the time is the period. So I get this new equation for velocity that's 2 pi r over t. And if I go back to the previous slide and I say, well, frequency is the inverse of the period, then I get another equation that velocity is 2 pi fr. So there's two different ways to find the instantaneous velocity as the object goes around in the circle. So the instantaneous velocity is going this direction, but based on the period and the frequency and this radius, I can tell you how fast it's going. Then the last step, so this is just getting us into some quantification stuff. I know that this centripetal acceleration is v squared over r. If I take my two equations for velocity and plug them in from the last slide, I get two more equations for acceleration. So really, we just made a huge bank of ways to quantify it, which means really nothing to us yet, but until we actually start talking about it, but just want to have a few different ways to quantify motion. Now, there's one more way to describe how fast something moves that's independent of where that object is on the circle, and that's its angular velocity. And if you've taken pre-calc, you've probably dealt with angular velocity a little bit. We're going to do very, very, very little with it right now, but we're actually going to come back when we do rotational motion and talk a lot more about it. So when something's moving in a circle, we can describe how fast it's moving or rotating in radians per second. From trig, 1 revolution is 2 pi radians. So this actually gives us two more equations. Like I said, we'll use this very limitedly right now, but we will come back to it a lot more later on in Unit 5. So just to give us one quick conversion example, if I want to go 55 revolutions per minute to angular velocity, well, 55 revolutions in 1 minute is RPMs. But angular velocity is measured in radians per second. So 1 minute is 60 seconds, and 1 rev is 2 pi radians. And if I go ahead and plug that into my calculator, I get about 5.76 radians per second. So it's a different way of quantifying our circular motion. So this is saying how fast it spins. This is saying how fast it's spinning, which might say the same thing, just in a different way. All right, so we got one quick example problem, and it says an audio CD has a diameter of 120 millimeters and spins up to 540 revolutions per minute. When its CD is spinning at its maximum rate, how much time is required for 1 revolution? And if we have a speck of dust riding on the outside edge of the disc, how fast is it moving? What is the acceleration? So this question is actually giving us a lot of information and asking us a lot of questions. So just to set up a couple things, it says that our radius is 120 millimeters. It's diameter. Well, then that means the radius is 60 millimeters. But we know right away that that's not a very good thing to take a look at. That is instead 0.06 meters. 500 RPMs, 540 RPMs. Well, that's a type of frequency, but normally we don't want to deal with things in minutes. So I'm actually going to convert that to our period, which is how long it takes to go around once, which is 540 revolutions in 1 minute. And 1 minute is, of course, 60 seconds. So I get a frequency of 9 revolutions per second, or we call that 9 inverse seconds, but that's going to be our frequency, and we'll use that to solve for the period. And then we're also we're looking for time, we're looking for velocity and acceleration. So with a couple little background, let's go ahead and take a look at that. So here, once again, I'm solving for my revolutions per minute, or my frequency, and also I did my diameter right there, and we'll use that on the next slide. And to solve for this then, time for 1 revolution was one of the first questions. That's our period, and we said that our period and our frequency are inversely related. So I just take 1 over the frequency to get the period, and it's 0.11 seconds. The next question was, how fast is the speck of dust moving? That's its velocity, and I have a bunch of equations now for velocity that I can think about, and I chose to use this one, but we could also use the 2 pi r over t to solve that as well. But then I just plug in, and I get 3.4 meters per second. So if you think about it, taking a look at the top down of a view of this is a CD, believe it or not. It could be whatever kind of CD you want. But if I'm a speck of dust right here, I am traveling at 3.4 meters per second. Now we'll talk later on this unit and a different unit. How does that place compare to this place? And going from the outside edge to the circle, how does that change how fast you're going? Well, just a little spoiler alert, if I think about this is the distance that this one travels, and this is the distance that this one travels, but they do so in the same time, this place on the outside edge is going to have a much higher velocity. We'll talk about that a lot later. And then finally, the acceleration, using our equation for that, we get 190 meters per second squared, which is actually really, 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 really large. And if you think about that, that's how the humid centrifuge works, and we'll talk more about that this unit as well. But other than that, that was your quick introduction into circular motion. We're going to spend a lot of time talking about how we use forces to quantify circular motion, as well as some of the other applications of it in dealing with things like weightlessness and planetary motion as we build our concepts throughout Chapter 6.